Okay, we continue this real analysis first. Now see, we have seen the functions, well about our functions. So we continue with next point, that is the mathematical induction. So real ordering principle, very important principle, and looking to be very simple. So every non-empty subset of set of natural numbers contains a least element. So wording may be different here. Every non-empty subset of n has a least element. So a more detail of this property is as follows: if S is subset of set of natural numbers, and if S is not equal to 5, understand this one. This is not equal to symbol. Then there exists m belongs to S such that m is less than equal to k for all k belongs to S, where m is the set of natural numbers. So this is the well ordering principle, and this is a very important one. Now see, principle of mathematical induction. We have seen in 11th or 12th standard the principle of mathematical induction. So in detail we have to study it now. So see, the statement of this one is, let S be subset of n and that possesses two properties. First is 1 belongs to S, and for every k belongs to n, if k belongs to S, then k plus 1 belongs to S. Then we have S is equal to n. That is, see the statement, if let S be subset of n and that possesses two properties. First is 1 belongs to S, and for every k, that is if k belongs to S, then if k plus 1 belongs to S, then we say that S is equal to n. This is the principle of mathematical induction. So principle of mathematical induction, second version of that is in this way. Let n naught belongs to n, n naught any natural number belongs to n, and let p of n be any statement for each natural number n greater than equal to n naught. Suppose that the statement p of n naught is true, and for all k greater than equal to n naught, the truth value of pk implies the truth value of pk plus 1. Then pn is true for all n greater than equal to n naught. So this is the if you don't get this clear understanding about this one, in example we see that what is that second version of principle of mathematical induction. Now there is one more principle of strong induction. Let S be a subset of n such that 1 belongs to S, and for every k belongs to n, if this 1, 2, 3 up to k is subset of S or belongs to S, then k plus 1 belongs to S. Then we say that S is equal to n. So here is an example, that is for each n belongs to n, prove that 1 plus 2, 3 plus up to n is half of n into n plus 1. We know that sum of first n natural numbers is n into n plus 1 upon 2. So how to prove it using this principle of mathematical induction, we have to learn here. So we have to prove this one. So let me take n is equal to 1. If n is equal to 1, then left hand side contains only 1, and so left hand side is 1, and right hand side is half of 1 into 1 plus 1 means 2. So 2 to get cancelled, it remains to be the 1. So left hand side is equal to right hand side. Therefore, the result 1 is true for n is equal to 1. Okay. Now assume that k belongs to S. That is to assume that above result is true for n is equal to k. Means sum of first k natural numbers is k into k plus 1 divided by 2. To prove this result for n is equal to k plus 1. Okay. That is, here we assumed the result is true for n is equal to k, and we have to prove it is true for n is equal to k plus 1. Okay. So left hand side is 1 plus 2 plus 3 up to k plus 1. We have to prove sum of k plus first k plus 1 natural numbers is k plus 1 into k plus 2 upon 2. So see here up to this one. So 1 plus 2 plus 3 plus k plus 1. So we know that sum of k is k into k plus 1 divided by 2 plus k plus 1 is the last number that added here, and simplifying this we get it is k plus 1 k plus 2 divided by 2. So result is true for n is equal to k plus 1. So if result is true for n is equal to k plus 1, therefore by principle of mathematical induction, the above result is true for n belongs to n. The proof of this result by using principle of mathematical induction. Okay. Similarly, this is the same by using the principle of mathematical induction. Okay. We see the different example. That is, given two real numbers a and b, prove that a minus b is divisor of a raised to n minus b raised to n for all n belongs to n. That is, we have to prove a minus b divides a raised to n minus b raised to n. So factorize म्हणजे आपण त्याला divide करू शकतो. To prove this one, a and b are real numbers and n belongs to n. So we prove it is for n is equal to 1 plus. So to prove a minus b is factor of this one. If n is equal to 1, clear a minus b is factor of a minus b. N is equal to 1 means it becomes a minus b only. Assume that result is true for n is equal to k, that is a minus b is factor of a raised to k minus b raised to k. Now we have to prove a raised to k plus 1 minus b raised to k plus 1 याचा factor a raised to k minus a minus b त्याचा factor आहे prove करायचा. So see simplified written here, a raised to k plus 1 as it is. We subtract a into b raised to k and we add a into b raised to k minus b raised to k plus 1 here. Here it is equal to this way, but actually plus 1, k plus 1 there. So from first two terms, let a get common. So it becomes a into bracket a raised to k minus b raised to k. From last two terms, b raised to k is common and in bracket there is a minus b. Since a minus b is a factor of a raised to k minus b raised to k, and clearly a minus b is a factor of b raised to k into a minus b. Therefore, a minus b is factor of a raised to k plus 1 minus b raised to k plus 1. So above statement is proof for n is equal to k plus 1, and so by principle of mathematical induction, a minus b is factor of a raised to n minus b raised to n. Meaning of this example is also that is to prove that a minus b divides a raised to k minus a raised to n minus b raised to n. Same example there. Now prove that 2 raised to n is less than equal to n plus 1 factorial for all n belongs to n. So how to prove it? Now prove this result for n is equal to 1. So if for n is equal to 1, the 2 raised to n becomes 2 raised to 1 and n plus 1 factorial becomes 1 plus 1 factorial means 2 factorial. Clearly 2 is less than equal to 2. This is equal here. Okay. So result is true for n is equal to 1. So we assume that result is true for n is equal to k. So 2 raised to k is less than k plus 1 factorial for all k belongs to n. Now we have to prove that 2 raised to k plus 1 is less than or equal to k plus 1 factorial. So 2 raised to k plus 1 is 2 times 2 raised to k. Clear? Which is less than equal to 2 into. We know that 2 raised to k is less than equal to k plus 1 factorial. So this is k plus 1 factorial. It is by 1. It is written since it is by 1. So which is less than equal to k plus 2 into k plus 1 factorial. Because k plus 2 is greater than equal to k for k belongs to n. Clear? So k plus 2 into k plus 1 factorial means it is k plus 2 factorial. Here this is important. That is k belongs to n means k takes the values 1, 2, 3 in this way. So 2 is less than or equal to k plus 2. Actually it is clearly less than 2 is less than k plus 2. So k plus 1 factorial as it is. So this k plus 2 into k plus 1 factorial means k plus 2 factorial. So hence by principle of mathematical induction, the inequality holds for all n belongs to n. So same, this is results. There are so many examples. Now this is the second version of principle of mathematical induction. The example depends upon that version. So prove that 2 raised to n is greater than 2 raised to n plus 1 for all n greater than equal to 3. We have to prove this result for n greater than equal to 3. So we have to take first n is equal to 3. So we get 2 cube means 8 and this is 2n plus 1 means we get 7. So clearly 8 is greater than 7. So result is true for n is equal to 3. Clear? Hence, the above result is true for n is it is true, actually true for n is equal to 3. Assume that result is true for n is k. So we get 2 raised to k is greater than 2k plus 1 for all k greater than equal to k, 3. So now we have to prove 2 raised to k plus 1 is greater than 2 into k plus 1 plus 1. So 2 raised to k plus 1 is written 2 raised to k into 2. We know that 2 raised to k is greater than 2k plus 1. So it is 2 times 2k plus 1. So this becomes 4k plus 2. 4k plus 2 can be written as 2k plus 2k plus 2. And this is greater than 2k plus 3. So because 2k plus 2 is greater than 3. Because k takes values 1 to 3. So value of this 2k plus 2 is 4, 5, 6 in this way. Okay. Sorry, 4. It is greater than 4. So 2k plus 3. 2k plus 3 can be written as 2 into k plus 1 plus 1. And result is true for n is equal to k plus 1. So mathematical induction आपण हा result prove करू शकतो. This result is true for n is greater than 3, greater than equal to 3. See, this result is not true for n is 1 and 2. So if we put n is 1, then it is 2, and this is 3. The 2 is greater than 3 is wrong. So this result is true for n greater than equal to 3. This is principle of mathematical induction. That is the second version of principle of mathematical induction. So there are so many examples. I will send WhatsApp to this PDF file. You can study it very well. One more example is prove that 5 raised to 2n minus 1 is divisible by 8. त्याला 8 ने भाग जातो हे प्रूव्ह करायचं for all n. So for n is equal to n, the value of 5 raised to 2n minus 1 is 24. We know that 8 divides 24. So result is true for n is k. Yeah, n is 1. So assume result is true for n is equal to k. So 5 raised to 2k minus 1 is divisible by 8. We assume it. Okay. And we have to prove that 8 divides 5 raised to 2 into k plus 1 minus 1. So that's why we simplify this. 5 raised to 2 into k plus 1 minus 1. It becomes 5 square into 5 raised to 2k means 5 raised to 2k plus 1, that is plus 2, minus 1 as it is. Simplifying, we get 25 into 5 raised to 2k minus 1, 25 into 5 raised to 2k minus 25 plus 24. That is minus 1 can be written as in this way. This is just adjustment to prove this result. So 25 into bracket 5 raised to 2k minus 1. This from first two terms 25 get common plus 24 as it is. And clearly 8 divides 24 we know. And we assumed that 8 divides 5 raised to 2k minus 1. Here we assumed that 5 raised to 2k minus 1 is divided by 8. So 8 divides 24, 8 divides this one means 8 divides total sum of these two terms, and the result will hold for all n. So in this way there are so many examples. So it is important now the countable sets. So under this article we shall discuss denumerable sets, countable sets, uncountable sets and their properties. The examples on denumerable sets and countable sets are discussed. So equivalent sets, that it is two sets A and B are said to be equivalent if two sets are equivalent if the function from set A to set B has one correspondence between the sets A and B. Okay. So we say this is the equivalent sets. Equivalent means not equal. Clear concept. Clear these two concepts: equal and equivalent sets. Okay. So equivalent sets मध्ये काय असतं की दोन्ही सेट्स मधले elements same असतील. Number of elements must be the same. And there is this means this is the one correspondence between the sets A and B. So countable and uncountable sets. A set A is said to be countable if it is equivalent to the set of natural numbers. If it is equivalent to the set of natural numbers. This means what? See now. See. What is the meaning of this one? So suppose set A is 2, 4, 6 ... in this way. This is infinite set. Then see, we know the set n, set n of natural numbers 1, 2, 3 ... in this way. Now set n means we know that, and a means here we have taken. Now see, set n contains the elements in this way, and a contains 2, 4, 6, 8 dot here also. Now when we say the set A is countable, that is there must be one corresponding between the set of natural numbers and A. That is, we can take the one correspondence in this way. 1 is related with 2, 2 is with 4, 3 is with 6, 4 with 8. By some law, whatever we do. So we say that this 1 is corresponding to 2 means 2 is first element of the set A, 4 is second, 6 is third, 8 is the fourth element, in this way. So we say in this way. This means the set A is a countable set. Okay. So see, the set A is said to be countable if it has equivalent to the set of natural numbers. Okay. And uncountable set is an infinite set which is not countable set. Okay. Thus, A is countable if there exists one-to-one correspondence between set of natural numbers and set A. The elements of set A are then images, that is f of x1, f of x2, f of x3 means A can be written in this way. Just we take that example once again, see what is that actually. So we have taken n the set of naturals, that is 1, 2, 3, 4, 5 and A the set that is 2, 4, 6, 8 in this way, and f is a function from set n to A. Then 1 is related with 2, 2 is with 4, meaning of that is f of 1 means 2, f of 2 means 4. Okay. So here is written. So elements of set A can be written as f of x1, f of x2, f of x3, f of x4 in this way. Do you get it? So then we say this is the countable set, otherwise not. Okay. So see the example. Show that the set of natural numbers is countable. To show that the set n of natural numbers is countable, we define function f n to n as f of n is equal to n. Clearly, all the values of the images f of n are natural numbers. Also, all the natural numbers are distinct. So f of n to n is 1, 1 and onto function. Here f is 1, 1 corresponds. Means that function must be 1, 1 and onto. And therefore, n is countable set. Set of natural numbers is countable. Keep in mind that is set of natural numbers is countable. Now see, prove that the set of integers is countable. Okay, I or z whatever may be. So we know the set of all integers includes 0, 1, 2, 3 and -1, -2, -3 with the set of all integers. So let me take the function here of n to I, natural numbers to this I, defined as in this way. F of n is equal to n minus 1 upon 2, written here in this way. Okay, this f of n actually this is n minus 1 upon n. This is for n odd numbers, odd integers, and this is f of n is minus n by 2 for n even integers, that is 2, 4, 6 . This mapping can be displayed by the enumeration as in this way: I 0, 1, -1, 2, -2, 3, -3 in this way. So above mapping, one gives bisection, that is 1, 1 and onto. 1, 1 corresponds of n onto I. Hence, the set of all integers is denumerable, means countable. So, do you get this point or not? I will explain it. So, so first, sorry, let me take pencil. So this is the n and this is the I, that is set of integers. We define function n to I. We know that n contains the natural numbers in this way, and integers are in this way: 0, 1, -1, 2, -2 in this way. Okay. So for n odd, that is if n is odd, f of n is n minus 1 by 2. That is, if n is 1, we get 1 minus 1 upon 1 means 0 upon 1 means 0. So 1 is related with this 0. Now 2 means minus n upon 2 there. So n is 2 means we get minus 1. So 2 is related with minus 1. 3 related with 2. See, 3 minus 1 upon 2. Sorry, 3 minus 1 upon if n is equal to 3, we get 3 minus 1 means 2 divided by 3. So f of n, f of 3 must be equal to 2 there. N minus 1 upon, so function is defined. Three minus 1, that is 2 divided by n. So for n is 1 we get 0, 2, for n is 2 we get, so n is 4 we get minus 2, 4 is minus 2. So for 3 we must get this 2. So 3 minus 1 upon 3, not 3 minus 1 means 2 divided by 3. So it must be 2. Okay. So n minus 1 divided by n, and this is right. This is n plus 1 actually. Here is n plus 1. That is, for n is 3, we get it is 4 divided by, not it is 4 divided by 3. This is also not correct. So it must be, for n, this is, so we must get that is 2, f of 3, f of 5. So this is not correct. So I will explain it later. F of n is n minus 1 or n plus 1, not it is for 1, 3, 5. We must get 0. There is some problem. So I will explain it later. I can get this formula. There is a wrongly written. So let me take one more example. Prove that the set of even and odd natural numbers are countable. Prove that the set of even and odd natural numbers are countable. So set of even and odd, that is E means 2, 4, 6 dot dot dot, and O means odd natural numbers. So E and O denotes even and odd natural numbers. So we define the functions as Fn to E by f of n is 2n, and Fn to O by g of n is 2n minus 1. So we get totally from this 1-1 correspondence. That is, if n is given in this way. So this is n and this is E. That is, f is a function from n to E. So dot dot dot, and E means even natural numbers. So we have seen this firstly. That is, f of n is 2n. So this one is in this way. F of n, f of 1 is 2, f of 2 is 4, f of 3 is 6. In this way. So there is one-to-one correspondence between the set of naturals and set of even natural numbers. Then we take odd. Then here it is odd means 1, 3, 5 in this way, 7 dot 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 in this way. Okay. So g of n is defined as g of n is 2n minus 1. So if n is equal to 1, we get 1. So 1. F of 2 means this is we get 3. F of 3 means we get 5. F of 4 we get it is 7, etc. So there is again one-to-one correspondence between the set of naturals and set of odd natural numbers. Okay. So We take the next example. Prove that union of two disjoint countable sets is countable. So, union of two disjoint countable sets is countable. That is, A and B are the sets in this way. These are the disjoint countable sets, means we know that intersection of these two sets is a empty set. So there is no common A and B. We count the elements of A and B as A1, B1, A2, B2, A3, B3, dot, dot, dot. The set A, B and B can be written as is a countable set. The union of two disjoint countable sets is countable. So remember the statement, union of two disjoint countable sets is countable. Okay. If A1, A2, A3 are countable sets, then prove that this is union. This is union. Okay. This is union. This is union. Union of n goes from 1 to infinity, is countable. That is, countable union of countable sets is countable. We remember the statement of this only. So, countable union of countable sets is countable. We are not going to do this one. Okay. Now, see, the set of rational numbers is countable. Now, important one. The set Q of all rational numbers is countable or denumerable. So, let En be the set of rational numbers with denominator n. So En can be written as in this way. So En, the set En is in this way. This is 0 upon n, minus 1 upon n, 1 upon n, minus 2 upon n, dot 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 in this way. So En is written in this way. Suppose as Fi to En is given by f of n is equal to 1 upon n. Okay, f of n is 1 upon n. So for n belongs to I there. Okay, n belongs to I. So means take down n belongs to I, not n. See carefully. So if n is 1, we get 1. We get 1. So n is 1 means E1 means we get one more set. E2 the another set. E3 असे सेट्स मिळतील तुम्हाला सगळे. ओके, E1, E2, E3. मग तिथे काय असेल त्यावेळी बघा. So n is 1 means f of 1 means 1 upon n means we get it is 1. Okay, E1 मधला 1 असेल. असे सगळे रॅशनल नंबर्स तुम्हाला याच्यात भेटतील f of n मध्ये. So f is 1, 1 and 2. So f is 1 to 1 correspond between en and I and are equivalent sets. But set of integers is countable. Therefore, en is a countable means set of rational numbers is a countable. Okay. So Q, the set of rational numbers, we can write Q means this is a union, this is union. Okay, this is union. Union of n belongs to 1 to infinity there. Okay, so en जो घेतलाय आपण en, तो en actually high. Okay, आणि मग मी मगाशी म्हटलं तसं E1 काय, E2 काय, E3 काय ते बघावं इकडे. आणि ह्या सगळ्या E1, E2, E3 अप टू इन्फिनिटी यांचं युनियन म्हणजे काय होतं तर Q म्हणजे सेट ऑफ रॅशनल नंबर्स. We know that countable union of countable sets is countable. That's why Q is a countable set. A very important example, how to write En and how to write that function. That is important one. Okay. So any subset of countable sets is countable. म्हणजे एखादा countable set आहे तर त्याचा सबसेट easily we can say this is countable, this is logic. Okay, so from this we take the next lecture for this. Again this is important. Closed interval 0, 1 is countable. No more, it is sufficient. This is again a small lecture. I will send it to